All right. So yeah, I'm happy to talk at Quilt Day. I think the last time I talked was summer 2019, so it's been a while. So I'm going to tell you about some work that I put in the archive.
I haven't introduced you. Everyone, this
Okay.
is Mark Wilde. We all know him, professor at LSU. Finger in a lot of pots. Today we'll hear about second law of entanglement dynamics for the non-asymptotic regime.
All right. Thank you. So yeah, happy to be back here at Quilt and hoping, the plan was for this one to have it in person, but then Delta variant wrecked that. So maybe for the fall, maybe we won't have hopefully we won't have an epsilon variant. So this is, I'm going to present it at the information theory workshop. That's going to be online. I think it might be hybrid. Some people in Japan will be there. Anyway, so it was recently accepted there. And let me get into it. So what do I mean by entanglement dynamics? So really, this is entanglement theory. This is a core part of quantum information theory that was established by this well-known paper of Bennett, DiVincenzo, Smolin, and Wooters in 1996. And we're interested in manipulating entanglement by free operations. In Marguerite's talk, you heard her talk at the end about resource theories. Well, a fundamental resource theory is the resource theory of entanglement. And there we suppose that two parties in distant laboratories share a two-party quantum state, and they're allowed to act on it with local operations and classical communication. So in this model, we assume that locally they have perfectly working fault-tolerant quantum computers, but then they're not connected by quantum communication channels. All that connects them is a classical communication channel. And then we want to know what kinds of entanglement manipulations can they do. I'm going to get into a bit of that later. Okay, so what is the definition of an entangled state? We define a state to be entangled by what it does not mean to be entangled. So a state is entangled if you cannot write it as a separable state. So a separable state has this form, a convex combination of product states. So here Px is a probability distribution, and these are sets of states. This is a state that can only be prepared by local operations and classical communication. So somewhere in the background, someone flips a coin or throws a die and reports the outcome of the coin flip or the die toss to Alice and Bob. And then conditioned on that value, they each prepare a state. And because there's no quantum interaction, all that they can prepare is a product state. And then if they somehow forget the outcome of the coin flip or the coin toss, then the state is this probabilistic mixture. And so this captures, this generally captures all that can be prepared by LOCC, local operations and classical communication. And so that's a separable state. And then a state's entangled if you cannot write it in this form. And related to some things that Marguerite was talking about in her talk, it's actually hard to decide if a state is entangled. If you're given the list of matrix entries that describe the state, we know that in a computer science sense, it's NP hard to decide if a state is separable or entangled. So that means hard for a classical computer. And then I had some work in 2012, which, the work with Marguerite we built upon. That work showed that it's hard for a quantum computer to decide if a state's separable or entangled. There are some fiducial forms of entanglement that we're interested in. And the most prominent case is a maximally entangled state of Schmidt rank D, okay? And why are we interested in that? Well, if you have an E-bit where D equals 2, then you can do teleportation. which is a great way to transport quantum information without actually having to have access to a quantum communication channel. And in fact, the teleportation protocol is what inspired people to think about entanglement theory, because then you start asking questions like, well, what can we do if a state is not perfectly entangled like this Bell state? You know, then you talk about entanglement distillation, and we'll get to that later. Now, if you have D larger than 2, then that's a greater resource, right? So if D's larger than 2, then I could teleport a quantum system of dimension D. There's a generalization of the teleportation protocol to dimension D. Another thing you can do with entanglement is superdense coding, right? So you can send, if you have access to a quantum communication channel, then you can double its classical capacity if you have access to EBITs as well. You can also generate secret key with the maximum entangled state. And so it's this very useful thing. Okay, a bit more detail about LOCC. What does LOCC look like? You imagine that Alice and Bob start with some generic bipartite state, and then it doesn't really matter that much who goes first, but let's suppose Alice goes first. She performs what's called a quantum instrument. That's also just a quantum channel that accepts a quantum system as input and outputs a quantum system and a classical system. And so then she'll send the classical data to Bob over a classical communication channel, and then she'll just store this quantum system locally. And that's where, in imagining LOCC, we imagine that they have fault-tolerant quantum computers, good working quantum memories where this quantum system can be stored. Okay, so then Bob gets this outcome of Alice, and then he does the same thing. Does a quantum instrument, sends classical data to Alice, stores this quantum system, and this goes on and on for some finite number of rounds. And the class of operations that this constitutes is called LOCC. And mathematically, we allow LOCC to consist of a finite yet arbitrarily large number of rounds. And if you're interested in more about LOCC, you can actually Google everything you wanted to know about LOCC. And then there's a nice paper that gets into a lot of more mathematical details of LOCC. This was published in Communications and Mathematical Physics. Okay, so starting with row AB, they do all this, and then at the end, they generate some state on these systems AN and BN. That's a state we'll call sigma A and BN. And so you can start asking questions like, given row AB and another bipartite state, can we transform rho to sigma exactly by means of LOCC, right? Can we do so approximately, right? And if we can do it approximately, how well can we do it? And then you start thinking of certain metrics to measure how well you did. So that's a basic question. And this is actually a basic question in any resource theory, given some initial and target states. Can we get from the initial one to the target one by means of a free operation? And there's all kinds of resource theories now where you can think about this question. You could also ask about a more Shannon style question. When I say Shannon, I mean Claude Shannon, who invented information theory in 1948. So if we instead start with n copies of the initial state, we can ask, what is the maximum rate at which we can convert n copies of rho to m copies of sigma? And you can ask about this being done exactly or approximately. And then a Shannon style thing would be, you think about a sequence of these protocols such that the error is tending towards 0 as the number n goes to infinity. Then you can ask about like, what's the maximum rate at which you can get sigma out of rho? Okay, so those are just some basic questions. In this talk, we're going to be focused on the non-asymptotic regime. So it's more like this and it's really the second question, rho and sigma getting from one to the other approximately. Now, to talk about approximate conversion, we need to think about measures. Standard measure, like Marguerite was talking about, or talking about as well, is fidelity. This is the definition for two mixed states. So you take the square root of the two density operators, multiply it, take the one norm. The one norm is the sum of the singular values of this matrix, and then you square that. And this is a standard measure used in quantum information theory. It takes values between 0 and 1. It's equal to 0 if and only if the states are orthogonal, perfectly distinguishable. And it's equal to 1 if and only if the states are identical. Okay. And then in between, it gives you a sense of how well one state can fake being the other if someone did a test to determine if one is the other. So the approximate transformation problem you can phrase as this kind of optimization. Given the initial state rho, the target state sigma, optimize the fidelity of conversion, right? So optimize the fidelity acting on rho with an LOCC operation. The fidelity of that state, this would be the actual state at the end of the protocol, right? So going back to this diagram, it would be like this. And the ideal target is this. When you look at this, indeed, it's an optimization problem. And then you go and look at this diagram and you're like, huh? How am I going to do this optimization? You know, we just defined LOCC as finite yet arbitrarily large. So it seems like that's going to be a hard optimization to do. And so, and also like the structure that you do a measurement, then a measurement, then a measurement, then a measurement is optimized over mathematically. And so what people have done, starting with Eric Rains and a number of people for the past 20 years, including Elisa and myself, that presented our work at the last quilt day. What we do is we relax LOCC to something mathematically simpler. And often what's done is you use what's called the positive partial approximation. And I won't get into the details of what that is, other than to say that is an important mathematical concept in this work with Elisa and in the work that I'm currently presenting. Okay. So let's talk about some basic questions beyond this approximate transformation problem. We said that EBITs are useful for teleportation. So then, thinking like Charlie Bennett et al. In 1996, we can ask about distillable entanglement. So how many maximally entangled states, or what dimension of a maximally entangled state can we recover from an initial noisy state by means of LOCC? So it's a different take on the approximate transformation problem. Here, what we're going to do is we're going to define one-shot distillable entanglement, fix the initial state, fix the epsilon, that's like the desired that you want, and then subject to those constraints, compute, make sure that the fidelity between the actual state of the protocol and the target maximum entangled state is larger than 1 minus epsilon. So subject to that constraint, then try to make D as large as possible. So try to get out as many EBITs as you can from the initial state, such that the fidelity is larger than 1 minus epsilon. And then if you do so, you can do you can send log D qubits up to epsilon 1 minus epsilon fidelity using teleportation. So that's an example of something you could do, right? or you could use them for superdense coding, or you could use them for key extraction, etc. Okay. In physics, we're always interested in reverse processes, so like here we're talking about a forward process from rho to maximum entangled. What about the reverse process? So starting from some maximum entangled state, how well can we make a target state rho by means of LOCC, right? So it's like we flip the task. But we think these entangled states are expensive, and so we want to minimize the cost. You can think of their cost as in terms of their dimension, like 2 EBITs are more expensive than 1 EBIT, right? Just kind of basic counting. So here instead, we fix epsilon, the desired accuracy, we fix the target state to be rho, and subject to that error constraint, we want the fidelity of the actual state of the protocol to be close to the target state, up to 1 minus epsilon. And then we want to minimize. And this quantity is called one-shot entanglement cost. So we have one-shot distillable entanglement and one-shot entanglement cost. And then the objective of this talk is to figure out a relation between these two. And the basic idea is going to be that the distillable entanglement should be less than the entanglement cost. Otherwise, you would have some kind of free entanglement generation factory, which is impossible, kind of just like by basic common sense, that you can't get something from nothing. You cannot get EBITs for free. Okay. Here are some pictures to visualize this mathematics. So the distillation problem, you can visualize like this. We start with rho AB. We allow Alice and Bob to do LOCC. This box represents, some complicated thing like this, where n could be arbitrarily large. And then we get these systems at the end, A hat and B hat. And then we want this actual state generated by the protocol to be epsilon close to a pure maximum entangled state with the dimension D as large as possible. Okay. Entanglement cost is the flip question, starting from the maximum entangled state, use LOCC to make rho AB up to epsilon accuracy. And then because EBITs are expensive, you want to make D as small as possible. All right. When do I stop? 250, is that it?
Yes, including 5 minutes for
All
questions.
right. Yeah, I think I should be fine. Okay, so let's get to the point. One of the basic principles of entanglement theory is that we cannot make entanglement from LOCC alone. We kind of emphasized that earlier. And then also, we cannot use LOCC to generate more entanglement than we already have. And the idea now is to make this quantitative for the non-asymptotic regime. So think about the maximum entangled state. What is its one-shot distillable entanglement? In the present work, what I did was to establish this upper bound on the one-shot distillable entanglement. So it's kind of a weird question because, like, here we're replacing rho AB with phi, and they're asking, well, how well can we get out phi? But the idea is to get out a larger dimension D of phi, but you're allowing for an epsilon error when you do so. So if you allow for an error, there's a trade-off. You can try to extract more out, right? And so what you see is that, well, if the error is 0, you're already at phi D, and well, you're going to be you're not going to be able to get any more out than phi d, so you have log d. But now if you allow an error, you can try to get out a little more. And one way to do so is to use this protocol that is in Elisa in my paper that involves bilateral twirls. Okay, so we have this upper bound. So that limits, how much entanglement you can extract from an already maximum entangled state if you allow for an epsilon error. Okay. As we were saying before, intuitively, it should not be possible for distillable entanglement to exceed entanglement cost. The argument we're making is like that used in thermodynamics to exclude perpetual motion machines. So if it were not the case, if the distillable entanglement exceeded the entanglement cost, what could you do? Well, you could start with some amount of entanglement, distill some amount, and then you could cycle back and forth. And here's an example. You could start with phi d, use an entanglement cost protocol to extract some other state, and then do a distillation protocol to extract phi d. And if the distillable entanglement exceeded the entanglement cost, you get more out at the end than you invested. And that should not be possible. Okay. But now let's think about this quite quantitatively in the one-shot regime. Okay. So what I want to do, and the main goal is going to be, this is the main theorem of the paper, that the one-shot distillable entanglement is bounded from above by the one-shot entanglement cost, plus this correction term related to the error of transformation. Okay, so to establish this inequality, all you do is look at this kind of cyclic process, right? So you start from a maximum entangled state of dimension d1, okay? And then you do an entanglement cost protocol to try to make a state rho AB. And you allow yourself an epsilon 1 error, okay? So you make that rho AB, and then using that rho AB, you do an entanglement distillation protocol, okay? And you extract phi d2 up to epsilon 2 error. So if we now pick this d1 to be the optimal value of the entanglement cost, so everything would have logs on it now. So log d1 to be that optimal value. And if we pick d2 to be the optimal value for an entanglement, for this entanglement distillation protocol, then we're putting in log d2 here and log d1 here, right? So now if you examine this overall process is an entanglement distillation protocol for phi d1, right? And this previous inequality says that the distillable entanglement of this whole process, going from phi d1 to phi d2, with a total error of essentially epsilon 1 plus epsilon 2, this bound has to hold. So over here, this is the entanglement that you can distill from the whole process. That'll be log d2, right? And that cannot exceed what you invested, log d1 plus the correction term. And here the correction term is essentially epsilon 1 plus epsilon 2. That's the argument. That's the argument for the inequality. That's the basic intuitive argument. But then in the paper, we need a lot more mathematics to justify this. We have to justify this inequality and some other ones. But that's the basic idea. And it's the same kind of thing you consider like in a thermodynamic analysis with a cyclic process. So what do we find is that this intuition holds. The one-shot distillable entanglement cannot exceed the one-shot entanglement cost plus a correction factor. So, and this correction factor is precisely related to the total error accumulated in this two-step process. Okay, and so if you want for these errors to be small, then you can make this arbitrarily close to zero, right? And then you really say, oh, indeed, then the entanglement cost cannot exceed, sorry, the distillable entanglement cannot exceed the entanglement cost. But then if you allow for these errors to be larger, then the inequality is not as tight and it's not as relevant, okay? So that's the basic argument. And I call it a second law because it's exactly the kind of second law statement that you see in thermodynamics that prevents the existence of perpetual motion machines. So what happened was I put this, oh, we're not there yet. Okay, let me essentially wrap up. We can recover an asymptotic statement from the one-shot statement. I'll just be quick with this. The asymptotic distillable entanglement you define in terms of limits, same for entanglement cost. So if you take this one-shot inequality, apply these definitions, take the limits, you get this very well-known statement that the asymptotic distillable entanglement does not exceed the asymptotic entanglement cost. And part of what motivated this work actually is during the summer 2020, I was given a tutorial on entanglement theory. And I was wondering, like, how do people prove this inequality? And I didn't find anything. And so I wanted to prove it. And then I came up with this. And then I didn't, there's nothing like this for the non-asymptotic regime. So then I decided to turn into a research paper. So shortly after I posted my paper, these very smart researchers, Ryuji Takagi and Bartosz Regula, got in touch with me, and they were like, why didn't you do this for arbitrary resource theories? Why didn't you do this for channels? And I was like, well, I just wanted to make a simple statement. And so now that's what we have, you know, they put in a lot of work. It was like, I put this up and then the next day they sent me this 10-page manuscript. And we've been working on it since then and refining it and to say as much as possible. And so we're going to release that soon. Thank you.
All right, thank you, Mark, for that nice talk. So are there any questions for Mark on this?
I have a comment, Mark. Actually, you used the words entanglement, dynamics, and manipulation. And when you started with those words, I was actually I didn't know at all what you were going to speak, but I'm right in the midst of writing a paper in which we are using the words manipulating entanglement dynamics. But I see it as completely different because although you talk of dynamics, there is no time aspect to your problem. Sure. Or when you talk about perpetual motion machines, and then you say about LOCC, for instance, not generating entanglement, which is of course true. But our interest has been on real dynamics in the sense of time dependence. And so what we have just now, because the first experimental results we have from Urbasi Sinha's group that you know, so we are just writing it up because we have been able to show how you can change the time evolution of entanglement, so real dynamics, by LOCC or even LO, forget CC, just a local operation on either A or B. So I just wanted to comment that we are using almost the same words, but talking of entirely different things. And in your discussion of even perpetual motion machines, all of that has to do with time. And I see no time as relevant at all for your discussion.
So let me address that. And oops. So when we talk about this diagram, this is a general formalism, right? This incorporates arbitrary evolutions that you could ever think of. And so when we want to have a law, we want it to apply for arbitrary evolutions that we could ever think of, right? And so all of that falls within this framework, right? But and so what I want to know is precisely like, if I allow arbitrary LOCC, whatever physically could be realized ever, then what can I get from it, right? And that's what distillable entanglement is. And then the same for entanglement cost. And so when I want a law, I want it to apply to an arbitrary process. And of course, you can study particular dynamics of actual physical realizations and see how those go. But from the fundamental perspective, if I focused on a particular set of dynamics, then I wouldn't have a general law.
No, I agree, Mark. But my point is that if you introduce a time element, for instance, LOCC cannot change entanglement, but LOCC can affect the time evolution of entanglement. And that is a different part, which is not then in this picture that you are looking at, because what we can show is that you can actually use LOCC to extend entanglement, for instance.
Yeah. So indeed, I think there are many interesting things to study about entanglement, and but I wouldn't necessarily say what it's like entirely different, right? But you're studying a different kind of problem, right? So I think there were some other questions.
Yeah, I have, Mark, I have a question. So when you're talking about the non-asymptotic regime, you're talking about single copies of rho AB and psi AB, right?
That's right.
Sigma AB. So is there an explicit expression for the entanglement cost or distillation in terms of the matrix elements of rho AB, for example?
No. It is going to be computationally difficult to calculate entanglement cost or distillable one-shot entanglement cost or one-shot distillable entanglement. Typically what we do is we derive lower bounds and upper bounds that you can actually compute. But I think a number of people suspect that calculating these quantities will be uncomputable, if you phrase it as a computational problem.
So for the case of pure states, when I'm given an initial state and a final state, I can calculate the entanglement monotones. And
that you can do. Yeah, sorry, I should clarify. States are easy, quote unquote,
Yeah, my question was going to be that in that case, I can answer the question whether or not a transformation is possible, or if it is not possible with certainty, then what's the maximum probability with which it's possible? So in this case, we don't have an answer to that, is what you're saying.
Right. Oh, for pure states, expressions for the one-shot entanglement cost. This is something I should know. I don't. I mean, we definitely know it for the asymptotic regime. It's the von Neumann entropy of entanglement, as you probably know.
Mm-hmm.
But we have
I think Vidal's result on the entanglement of a single copy, that gives the optimal probability of a LOCC transformation between an initial state and
a lot of these things are known from before. I was thinking, like, do we have a question for the one-shot entanglement cost and the distillable entanglement of pure states? I think the answer is probably yes. But I don't know what that is off the top of my head.
Yeah, thanks.
We had a couple more questions. Ivan, did you want to place your question?
Yes, I think Arshad was before me, so maybe.
Okay, Arshad.
I will be quick. Thanks for that, Mark. So a quick question. So for the main inequality that you derived, is that inequality actually saturated for some LOCC that you know of, or?
I was curious the same thing.
So this is what I was mentioning. Oops. Yes. This inequality can be saturated. We have to make a little technical point that bring the D and the 1 over 1 minus epsilon together, and then you have to take a floor. okay? And then you can achieve it. And that's this protocol in Elisa in my paper. It's just like what you do is you take the state you start out with, embed it in a larger space, and then you do this bilateral twirl. So what you do is you'd embed it in a space of dimension d over 1 minus epsilon. And then you do this bilateral twirl, and then you'll get it. And the bilateral twirl is an LOCC.
Yeah. Okay, and I'm
So
assuming this is,
then-
as you said, is described in your paper with Elisa.
That's right. Yeah.
Yeah. If I may ask, the final inequality that you got, where the entanglement distillation is smaller than the one, yes, entanglement cost, is this also achieved with the same protocol, the saturation?
That's a good question. And I think the answer is no. Not necessarily, because you're doing this two-step process. Yeah, the answer is definitely no. You're doing this two-step process, right? Where you broke it up and the error breaks up twice. And so the error
Right.
breaks up twice and it like introduces this inefficiency. This inequality was just about one step where you have one error.
Exactly. Yeah.
But this one, there's two steps. It could be possible with some more clever reasoning to, yeah, I don't know. That's a good question. I'll stop there because I'm not sure.
Okay, but thanks for that, Mark.
Yeah, we may want to get to our next speaker. Yeah, so I guess if anyone else has a question, Mark, you could send him an email or something. And Sid, if you want to get your slides going. And do I stop or do I pause recording?